Hi, if you want to do any kind of molecular simulation, and then this is a video which should, hopefully, get you started. I'm going to step-by-step guide some of the most common ways of analysing and looking at molecules, but before we get started, you're going to need a few bits of software. First off, you're going to need ORCA. You're going to have to make an account on the ORCA forum. You're going to have to promise that you're using it for academic use, and frankly, if you're here, hopefully you are. If you're a student, either at a university or at a college, then you absolutely qualify to use it for free. Make an account, download the software, get it installed. You'll also need Avogadro, which is also free. And I also dabble in JMOL if you want to look at visualizing any of these systems' vibrational modes. All the links will be in the description to the video, and might as well get started. Okay, so the first thing we're going to do is we're going to set up a directory to carry out our calculation. Mine here is called aminopyridine, rather creatively, and we're going to open up Avogadro. So Avogadro has this big draw window here, which is probably the first thing you spotted, and then there's a few display options over here to the left, and then some draw settings. And the draw settings are selected because the draw tool is by default selected. Now to start off, I'm going to just change the background color because I find it hard to see things against a black background, so we're going to change it to a white background, and then hopefully that'll be easier for you to see on the video. So if we left click with the draw tool selected in this white space, what we'll do is we'll place an atom, and that was a carbon atom, and then lots of hydrogen atoms appeared around it. And that's because this element drop-down menu has carbon chosen, and then over here the adjust hydrogens button is highlighted. If we click and drag from one atom away from it, then we'll place a second atom bound to it. If we click another atom without clicking and dragging, then we will simply place an atom. But it's not to worry because we can then click and drag between atoms to add a bond between them. We're going to draw 4 aminopyridine, so I'll draw in the carbon atoms first. And then I'm going to change element to nitrogen, click and drag, and click and drag, and at the 4 position, this amine. Now these are all single bonds, as you'll see, and I need to change that to a double bond, so we go to bond order, select double bond, and then click and drag between the atoms, and you'll notice it doesn't matter that I've got nitrogen selected. I'm not overwriting the atom type, I'm just overwriting the bond. Now I didn't take too much effort in choosing where to place these atoms because I know that Avogadro has a very good auto-optimization tool. If I was to place these coordinates right now into ORCA, then to relax that would take a very, very long time because they're not anywhere near where they should be. However, if I do a quick relaxation with the Avogadro tool, that will greatly increase the speed of my quantum chemistry calculation. So if I click this auto-optimization tool here, you'll see the draw settings down here now change, and all I need to do is use the default settings, the UFF force field, 4 steps per update, and just click Start. And very rapidly you'll see all those atoms move into a position which is lower energy. This energy up here will be reported until it doesn't change anymore, and now it's fully relaxed. So I will click Stop. So a few other tools that we've got here is that we can select atoms individually if we want to do anything with them. And then we can use this, if we right click with that selected, it will deselect them. And this rather pleasing navigation tool will let us click and rotate and look at things from all angles. But this is a good starting point for our calculation. And what we could do now is we could go over to extensions and ORCA and generate an ORCA input. I, however, prefer to write my ORCA input files by myself. So what I'm going to do is I'm going to export these as .xyz files. So you go to File and Save As, navigate to your directory you're carrying out the calculation, save as type XYZ, and we're going to call it aminopyridine. Click Save, and then we can simply leave Avogadro and we have our XYZ file Next, we're going to write our ORCA input file. And to do that, we're going to use Notepad. With Notepad open, we'll start off by defining the functional. Now, the functional is the set of instructions, the method we're going to use to come to our relaxed structure. And we're going to put an exclamation mark and then PBE to use the PBE functional, which is a very good all-purpose functional. Now we need to tell it what we want it to do, and we want it to optimize the structure, i.e. relax the structure, and for good measure we should also ask it to calculate an infrared spectrum. Calculating the infrared spectrum is the key way to find out if your structure is actually valid. So we do that with the frec keyword. Finally, because we're using Avogadro, we should use the large print keyword, and this makes it so that the file is readable by Avogadro, and we can put that dot out straight into Avogadro. Now we're going to direct it to our XYZ file. We have to put two numbers here. The first number is the charge, it's uncharged, so we'll put 0. And the second is the multiplicity. The multiplicity is the number of unpaired electrons plus 1. So for example, if you have no unpaired electrons, which we don't, we have none at all, then we have a multiplicity of 1. But if you knew, for example, that your system had 1 unpaired electron, then you would put 2 in this field. If you had 2 unpaired electrons, you'd put 3, and so on. Finally, we'll put the name of the XYZ file we created, and then we go to File, Save As, and it's critical here that we change to an all files type, and we're going to save it as orca.inp. If you save that as an orca.txt, this will not work. You have to make sure it is an IMP file. Now we're going to go into the command line, and we're going to achieve that by clicking in this box here, typing cmd, and making sure that our working directory is the same as the directory where we've got our input file and our XYZ file. Now, we're going to type orca.imp greater than orca.out, and that's going to tell Orca to take our input file and generate a .out file. And what we'll see quite quickly is that lots of .tmp files are generated over here in this directory. And we're just going to wait until those files stop being generated and until this command ends. And with a little bit of movie magic, it's just finished. And you'll know it's finished because there are no .tmp files left, and all you've got is this relatively short list of files. We're going to have a look in the .out. It's the largest file by far because it summarizes all the data, and we're just going to double check that calculation happened as we wanted it to. So if we scroll down to the bottom, it should open in Notepad or any text editor. So we scroll down to the bottom, it says that Orca terminated normally. That's great news. I love it when it terminates normally. It doesn't crash or throw up errors. Incidentally, if there are errors, likely because your .imp file is not quite right, so double check your charge and multiplicities. And the total runtime was about 5 minutes. So if we scroll up, we'll see there's various entropy and enthalpy terms. Now these can be really useful if you're trying to do some calculations, such as theoretical pKa's, or if you want to look at bond formation, as like in some of my other videos, and then this enthalpy term is really useful. But we're going to go all the way up and we're going to check the infrared spectrum. Now I know we've just scrolled past one. You need to keep going up past these displacement modes and check this section here, this vibrational frequencies section. And what's really important is that we take a look at here and make sure there are no imaginary modes. Now an imaginary mode is a vibrational mode with a negative frequency. And if you think about that for a second, that doesn't make any sense. A negative frequency would mean that it was outputting IR radiation rather than absorbing it. A negative frequency is only possible if you've not got the fully relaxed structure. So if you see any imaginary frequencies here, then what you need to do is you need to tweak your input structure just a little, give something a 5-degree twist, or a little bond length adjust if possible, and then resubmit it. And you can do that with JMOL or with some of the tools in Avogadro if you wish to set a bond. And what's great is that we don't have any imaginary frequencies. Now, what we're going to do is we're going to close this, and we're going to look at Avogadro to visualize our results. So we'll open up Avogadro as before, and this time, rather than draw a molecule, we're going to take this orca dot out and simply click and drag. And you'll see that it loads the structure, but over here to the right, there's a few extra features going on. First off, we've got this orbitals list, and this orbitals list is quite long. It starts off at the LUMO, that's the lowest unoccupied molecular orbital, plus 102, which is not really relevant. Most of the time you want to be looking at the HOMO and LUMO. So we'll scroll down here and we can see that the HOMO here is at about minus 5.3 electron volts. And if we click on this with the surfaces thing over here checked, then you'll see this is what the highest occupied molecular orbital looks like in aminopyridine. Quite interesting, quite strange. You can also look at the surrounding orbitals, and this one maybe looks a bit more familiar. This looks like some p orbitals and the carbon atoms not overlapping and repelling each other. If we go down to the HOMO orbitals, then we'll see here we have a pi bond, 2 p orbitals overlapping. And you can look right the way up the list, and if you wish to look at some very should we say, high energy or exotic orbitals, then you can do so by clicking on Render. These have very strange geometries in the high energy, and if you go down to the very, very low energy orbitals, then these are essentially the same as an XBS spectrum. So this HOMO here, this will render mostly on the nitrogen, and this one will render on this nitrogen. Likewise, these will be core carbon orbitals. But like I say, you're going to be spending most of your time close to the HOMO and LUMO. And if you find an orbital that you think looks really attractive and explains a molecular property that you really want to try and talk about a bit more, then you may wish to take an image of this. So using this navigation tool, rotate the structure to the orientation you want, configure the orbital as you like, so you can maybe try a very high quality rendering. If you click render again, then it will improve the polygons and the general appearance of the orbitals a little bit. You can also adjust how much you want to show. So if you change this to a 4, for example, click render, then it'll make them a little smaller. And then once you've got the orbital that you wish to show off, you go to File, Export, and you can make a graphic or a vector graphic file, which you could then put in your report or simply save for a cool screensaver. The other thing that we can do easily in Avogadro is that we can look at the infrared spectrum. If we click this here, we can show the spectrum itself. And if you go to Advanced and go to Infrared Spectra Settings, then we can change things like the Gaussian line width, see how realistic it should look, and we can also choose to have labels on or off. Scrolling in this will zoom in and out of the window. Now this is great for a first look, but this is not how I would go about generating a figure for a report. The way that I would make an infrared spectrum is outside of Avogadro. Something else I'm going to do is I'm just going to revise how to visualize some of these vibrational modes. So let's just take a note. We've got a really strong peak over here at around about 380. And then over here we have a really strong peak at around 1624. So let's close this. Thank you, Avogadro, for being so good at visualizing orbitals and giving us a quick look at the vibrational spectrum. We'll close Avogadro really quick. and we can discard all the saves. So to look at the infrared spectrum and to output that as a useful data, we're going to use orca _ map spc. We're going to direct it to orca.out, and we're going to ask for an IR spectrum. If we hit enter now, it will quickly output us this .dat file. And if you click into here, then you'll see that it's just a plain text file, which is the full spectrum. And you can put this into software like LibreOffice, or Python, or Origin Pro to make a nice figure that you can fully control and put in your report. The next thing I said we're going to do is we're going to look and visualize these vibrational modes. Now, I have shown you how to do this in my water series, but just for a reviser, have a look back in the orca.out file, and we're going to go back to the vibrational modes section. And we know what modes we're looking at. We are looking for the modes which have vibrations around 380, which is mode number 9. And we want to look at the vibrational mode 1629, which is 32. So what we do is, again, in the command line, ensuring we're in the correct directory, we will type orca _ pltvib, plot vibrations. We'll direct it to orca.hes, and we're going to list, with a space in between, the orbitals we want to look at. So that's 9 and 32. And it will generate some .xyz files here. Now, I personally prefer to use JMOL to look at these. So let's open up JMOL. It's a great little tool. And we'll click and drag one of these XYZ files in. Here we have our 4 amino pyridine as expected. And if we go to Tools and Atom Set Chooser, then click this play button, then we'll see that this vibrational mode appears to be mostly this bending mode of these NH bonds. Now if we click and drag one of the other files we generated into here, and we'll replace the current model, then we'll see that this is the vibrational mode. This is what's happening at 1629. And quite pleasingly, if we take this amplitude slider, we can make it a little bit more reserved, maybe a little more realistic. But if we really want to demonstrate what's moving, we can crank it up and we can make these atoms do all sorts of silly dances. We can also change how fast they move by changing this period slider here. So, thank you JMOL for letting us visualize that structure. Now, there's one last thing I'd like to do, and that is to do a UV spectrum. Now, to do that, I'm going to need to make a new directory, and I'm going to make a new folder here, and I'm going to call it TD-DFT. That stands for Time Dependent DFT, Density Functional Theory. And we're going to copy in our orca.xyz file. So Control C, go into here, Control V, and I'm going to rename it amino pyridine. It's the output structure. Be really careful to use the orca.xyz. That's the relaxed structure. That's really important. Don't use the original amino pyridine structure. So back to the TD-DFT structure directory, and we're going to make an orca input file again. This time we're going to set it up for TD-DFT. So we'll start off again by defining the functional, and now we're going to set up the TD-DFT calculation. And we do that with percentage TD-DFT, and we're going to set the following parameters: nroots 50, max dim 5, end. These are the default parameters for a time-dimensional functional theory experiment, and it basically says how much you are allowed to move the atom by and move the atoms by, and how much energy that you're expecting to put into your system. These have been fine for every system I've studied to date. You may find that you need to tweak these, but definitely start with these and see if they match your use case. Finally, we'll direct it to the XYZ file. Again, 0 and 1, 0 charge, and it's a singlet, its multiplicity is 1, and then amino pyridine.xyz star xyz. File, save as, and this time make sure that it's all types, and we're going to save it as tddft.inp. And we can close this. So now in the command line, which again you can access by clicking in the Explorer bar and typing cmd, in the command line we will type ORCA, because we are going to be using the ORCA software, tddft.imp greater than tddft.out, and we'll hit enter, and just like in our previous calculation, lots of TMP files are made as the calculations are churned through. Now, that was a lot quicker than our last setting. Let's just have a look in tddft.out. We'll just make sure at the bottom, fantastic, ORCA terminated normally. So, let's go back to Avogadro and we'll have a look at our tddft and the UV spectrum that it generates. So if we reopen Avogadro, again click and drag in this tddft.out, and this time we're going to see that there are no orbital informations here, and that's because the calculation we did was quite a lot simplified. But if we go over here to extensions and spectra, then we'll find that by default we can load this UV spectrum. And if we go to advanced and UV settings, you'll see we can choose a Gaussian width here. And so we can set the parameters whatever we like. Now we're expecting mostly these bands to be quite high energy. So this is a aromatic organic species. These are mostly pi to non-bonding to pi orbital transitions. But we can get an idea of the structure of this UV spectrum. Bear in mind these here, 100 to 250, these are all way out of the visible range, so these are UV transitions which you will not be able to see with the naked eye. So just bear that in mind when considering this kind of spectrum. But this lets you simulate the UV spectrum for various species, and so you can see what, for example, adding a nitro group or multiple nitro groups, or even changing the protonation state, or adding sodium atoms or more nitrogens within the aromatic ring could do to this band. Likewise, if we ever want to export this spectrum, which you may well, if we close Avogadro here, then if we go back to the command line, we can export the spectrum just as we did with the infrared, orca _ mapsbook, orca tddft.out, don't make that mistake, and abs. Make sure you put the right number of D's in there, and then you'll see it will output this DAT file. This has several rows in it. Depending on your ORCA version, each one will be slightly different, but my understanding is that the first row here is the actual absorbance data. If I'm wrong, feel free to tell me in the comments what the correct row to use is, and I'll update in the description. Now the last thing I want to talk about is the other information you can get from this calculation. So if we go into the tddft.out file, then what we'll find is around midway through, we'll see this excited state singlets list. And this is a list of all the transitions and the states that are involved in their formation. So for example, this transition here at 3400 wave numbers, bear in mind this is not by default nanometers. You will need to convert that into nanometers if that's the unit you prefer to work with. But you can see that this state is primarily made up by about 74% of a orbital 24 to orbital 25, and there's a small amount of orbital 23 to orbital 25. And if you take a look down here, you'll see that many states are summarized with the electronic transition energy listed here, and with the states that give rise to them listed here. And so this is a tool for letting you understand what transitions are occurring in some dyed or coloured chemical species. So hopefully that's given you an idea as to how to get started doing some computational chemistry by yourself. These calculations took me less than 6 minutes of actual computer time, and my PC is not high-end anymore, so yours may well go faster and more effectively. Likewise, if you're working on an older machine, genuinely, I don't think these will present any issues, and I just wanted to show you that you can study molecules and do a little bit of chemistry, even if all you've got to hand is a laptop. All the software is free, and it's begging you to go out there and get to use it. And, little word to the wise, even in today's age of AI and high programming, computational chemistry and understanding what's going on with molecules has never been more relevant and is quite a lucrative skill set. So practicing with this, doing your own tools, really can't do you any harm. Anyway, if you've watched this far, thank you very much. I love running this channel. Any questions, any problems, drop those bad boys in the comments. I always try to respond at least within a few days. Goodbye.